In this video, I want to talk about how we can use this notion of representing a vector as a vector in Rn and isomorphism between vector spaces in Rn to actually solve problems. Right now, it might feel like some super abstract thing, but it turns out that it's really useful and allows us to take everything we've done with Rn in terms of span, linear independence, and basis and use it to answer questions in other finite dimensional vector spaces that aren't Rn. There are two things I want to show in this video. First of all, if we're going to use this to solve problems, we need to know how to actually represent vectors in terms of a basis. And so that'll be the first thing I'll do, is give you two examples where we can figure out how to find rep B of V. And then I want to take our ability to do that and apply it to answering questions about span, linear independence, and basis in spaces other than Rn. Sometimes when we're trying to represent vectors in terms of a basis, there's no calculation involved at all. If you understand what representing in terms of a basis means, you can just write down the answer. And if you don't understand it, it's going to be impossible. This is one of those examples. So here I'm working with P3, and I'm working with one of the natural choices of basis. Remember, order matters for these bases. And this choice is x cubed, x squared, x, and 1. And if I want to represent a vector in terms of that basis, as long as I understand what this means, I can just do it. Representing a vector in terms of a basis is asking, what are the coefficients when I write this vector in terms of that basis? Write those coefficients down as a vector. And here, because of the choice of basis, the coefficients are just 1, 2, -1, and -7. This happens not infrequently, actually, where, generally speaking, we want to choose bases that are easy to work with, right? Where we're not trying to make our lives hard. We're trying to make things as easy as possible. And it's very natural working with P3 to choose this basis. And if we choose that basis, it's really straightforward, once you understand what you're supposed to do, to represent a polynomial as a vector in R4. You just write down the coefficients. Other times, it's not quite so easy. Actually, in the example I'll show you, you could notice that there's a pattern. But generally speaking, if our vector space is a bit more, I don't want to say complicated, but if our vector space doesn't quite have this nice structure here, right? Our vector space here was defined in terms of the coefficients, which made it pretty easy to think of it as R4. It can be a bit trickier. So here we're going to go back to this same vector space we were considering, the set of solutions to x minus 3y plus 2z equals 0. And I claimed in the previous video that we could represent this vector u in terms of this basis, and I just kind of wrote down the answer, but I want to show you how I go about finding that answer. What I need to do is I need to write the vector I'm trying to represent. So here I'm trying to find rep b of this vector u. Need to figure out what that is. In order to do that, what I need to do is I need to write u as a linear combination of v1 and v2. How do I solve this? Well, let's write out what this looks like. This is a vector equation, a linear vector equation, and we know that linear vector equations are equivalent to linear systems. And so what I need to do is I need to solve this augmented matrix given right here. And my solution ends up being that A is 1 and B is 2. I'm not going to go over how to solve this. This is something we've covered in previous videos. So this is what we end up getting. A is 1 is B is 2. And so that means that u is v1 plus 2v2. You should always check your work when it's easy. This is an easy thing to check, right? Just confirm that if we take this vector and then we multiply this by 2 and add it, we get this vector. And that means, now that we've written this in terms of the basis, that we know what rep b of u is. It's 1, 2. So two main situations finding rep b of u. Sometimes you can just write it down because of the nature of the way your space is defined and the basis that's been chosen. Sometimes you have to work a little bit harder, but it's still not anything new. You have to figure out how to write the vector of interest as a linear combination of the basis vectors that you're working with, and you can do that by setting up a vector equation that will give you a linear system. And even if these original things weren't vectors, if they were like polynomials or something, you could still set up a linear system that would allow you to write these as linear combinations. All right, that's how we find rep b of v. How do we use it to answer questions about span, linear independence, and basis? Let's go to an example, and I'll work with P3 again because the process of converting to vectors in R4 is so fast, right? Because it's straightforward. Okay, so I have a set of 3 polynomials, and I want to know, are these polynomials linearly independent? Do they span P3? And do they form a basis for P3? And to answer this question, what I'm going to do is I'm first going to represent them as vectors in R4. So I'll find rep, I'll choose a basis. I'll find rep b of v for each vector. So our first vector is 1, 0, minus 1, 5. Our second vector is 2, 1, 0, 8. And our third vector is negative 5, negative 1, 3, negative 23. So I found rep b for each vector. Here I could just write it down. And now I'm going to answer those questions for this set of vectors. So I'm going to say, is this set of vectors in R4 linearly independent? Does it span R4? Is it a basis? We can answer 2 of those questions right away. These are vectors in R4. There's only 3 of them. That means they don't span R4 and they don't form a basis. So that means that these 3 polynomials do not span P3 and they do not form a basis. It's still not clear whether they're linearly independent. So let's go through that process. How do we do this? We write our vectors as the columns of a matrix. And we convert that matrix to reduced row echelon form. And I'm not going to go through the process of actually doing this conversion. I'll just tell you what we get. This is the reduced row echelon form. When you work it all out, you can confirm that. And what this means, we're interested about linear independence. The question is there a pivot in every column? And there's not a pivot in every column. So they're not linearly independent. So this set of vectors, to get it all on the screen, in P3, we represented them as vectors in P4, and we've determined that the vectors in P4, we represented them as vectors in R4. We determined that the vectors in R4 did not span R4, did not form a basis, and were not linearly independent. That means that these original vectors have those same properties, because those are vector space properties. They're not linearly independent. they do not span the space, and they're not a basis. Let's look at a second example. So the vector space, the set of solutions to this linear equation, you can choose any basis you want, but the basis we've used previously was this, and so I'll use it again. And I want to answer these questions about these two vectors. So first, let's verify, or do this on your own. These are in fact solutions to this equation, and so they are vectors in the space. My question is, do these two vectors span the space? Are they linearly independent? Do they form a basis? And you can get tripped up here if you're not careful. You might say, look, these are vectors in R3. There's only two of them. They don't span the space. But that's not correct, because we're not asking if these two vectors span R3. We're asking if they span the subspace of R3 given by this plane that we looked at, right? The set of solutions to this linear system. So what are we going to do? We're going to represent these as vectors in R2. And you would do this using the process that I just described. You end up getting the following. And you'll notice that, in fact, because of the way that the basis was chosen, the representations of these vectors in this specific example always just end up being the final two entries. But that's in some sense a coincidence. I mean, it does often happen with these linear systems that there's a pattern, but you would have to find it each time. It's not always the same sort of thing. Okay, so we have this representation in R2 of each of these vectors, and now we need to answer the questions that we're asking about those vectors. Let's add a little space here. So we need to figure out, are these two vectors linearly independent? Do they span R2? Do they form a basis? And now we see, okay, wait a second, this is two vectors in R2. So the answer is not obvious, right? These could form a basis, they could span, they could be linearly independent, or maybe not. And so what we have to do is we need to write down our matrix by writing these as the columns. We need to convert to reduced row echelon form. Now we have a pivot in each row and each column, and so that means that these are linearly independent. They do span R2, and they are a basis for R2, which means that our original vectors are also linearly independent. They span the vector space V, this space that looks like R2, and they form a basis for V. All right, so hopefully those examples were helpful. In each situation, you're going to have to work with a different basis. And the nice thing is that whatever basis you choose, as long as you do the math right, it'll work, right? I could have chosen a different basis here. Right? I didn't have to choose this. Maybe in my solution, I kind of ended up with some different basis. That's fine. Here, I'm not really sure why you would choose a different basis other than maybe ordering in the opposite order. But let's say I were working with a different basis. I could still do all this process, and the intermediate calculations would be the same, but the ultimate answers, are they linearly independent? Do they span the space? Do they form a basis? That would not change.